I'm Megan Rudo. I'm an electrical engineering student at Purdue University. So as I'm sure we're all aware by now, the construction industry is behind other fields in the technology and innovation. They also have a lot of very dangerous occupations. There's a lot of injuries, and it becomes very costly when mistakes are made. So our solution is to use robotic process automation, also known as RPA, for the process of building timber frames. We're building a modular end effector for robotic arms. Professor Zhang has patented this technology. And so my project for last summer was to start the process of building the physical prototype. So why RPA? It's time saving. It's faster than the human building speed because they automate those processes and they don't have to deal with as many human mistakes. It's also very cost effective. There's less wasted materials. So the objectives. The first thing is to build the working prototype of the patented timber frame end effector and to demonstrate feasibility for potential industry use. So we divided this up into different work breakdowns. First was the design. Most of the design was given to me by previous researchers, so my job was to adjust those designs to make them capable. Then the manufacturing portion, building all those pieces and then assembling them was the next step. Then working with the electronics, we worked with the KUKA robotic arm. And then the programming of it to get it working fully functional for industry use, and then the documentation. You can see on this slide here, we have the CAD of the project we were working on. So we have that big KUKA robotic arm, that's all the dark gray. And then we added a pneumatic suctioning plate on the end to pick up the timber frames. Then there's an elbow joint to move those frames around and a nail gun on the end to build it all together. So for the design, the first thing I had to redesign was the wrist mount. That is the piece connecting our end effector to the KUKA robot. That one had to be completely flush because of the way the KUKA is mounted. You have to put those screws into those big 6 holes on the side. And without it being flush, it cannot be properly mounted and secured. Then for the bearing case, we're essentially building our own bearing. So I had to split that into halves and then adjust a few more of those pieces to be able to put all of the greased up metal balls in there to get it to be able to spin. The motor mount had to be adjusted. We have a bunch of motors that we are using on this, and they have to be mounted properly so that nothing flies away and that everything is secure. I also had to work on the bearing mount. And then the nail gun mount had to be completely designed. So I tested 2 different orientations of it to find out which one would be the most cost effective to build and which one would last long term, since this is going to be, you build a lot of wooden frames when you're working in construction, so which one would last the longest. You can see those 2 orientations on the side there. For the manufacturing portion, a lot of these pieces were 3D printed after they were modeled in CAD. I did a 60% gyroid infill because I find that to be the strongest under stress and under the tension. And then a PLA plus filament of 1.75 millimeters was chosen due to it being stronger than general PLA, but not as costly as some of the other, like the PETG and the other filaments. For the assembly, you can see the bearing case on the side. That one I had to insert. There's a bunch of metal tubes that you can see in there. That's what's holding it all together, as well as a bunch of screws on the top. And then all those metal balls that I mentioned that have to be greased up in order for it to spin smoothly. And then the elbow arm, which we saw in the original picture, those screws on the side that needs to be cut down or else they're a hazard. And then mounting it to the hollow aluminum tube. And then you can see the motor mount on the right. That one has a bunch of different 3D printed components to it. The piece that I had mentioned before is not in this picture. That's what gets slotted on the very top where that metal is showing. So the results, you can see what has been currently attached to the KUKA. All those pieces that I had previously showed you are not currently attached because they need more adjustments and more things need to be made. So this is our current build. It's a partial assembly of the components partially mounted to the KUKA, but there are a lot of future recommendations for the electronic integration working with the KUKA as well as the electronics within this. We have a bunch of encoders and sensors that need to be added on. We also need to finalize and build the nail gun mount design. And then program the robotic arm. The KUKA uses essentially a teach engine. It's like a low code solution. And then we need to evaluate the performance and make sure that it is suitable for industry use and that it is not dangerous. Thank you.